Greetings. I would like to talk about the associative property for scalars with matrices. And we are going to do that by naming a few example things. We're going to name an example scalar and a couple of example matrices. If you don't remember or you're unfamiliar, a scalar is just some number, a real number, and a matrix is a two-dimensional array of elements. In this case, we have both these are two-dimensional arrays of real numbers. And we want to explore what happens when you try to multiply scalars and matrices. One of the first things that we have to remember is that we have to make sure that our matrix multiplication is defined. So we will look at that. I want to explore scalar K times matrix A times matrix B. Since we have matrix A times B, we are going to look at the dimensions of these two things. I have a 2x3 matrix for A, and I have a 3x1 matrix for B. We look at these inner two numbers, and that's our check. If they match, then we know that multiplication is defined for this. The outer numbers will be the dimensions of the product matrix. So our product, when we multiply matrix A times matrix B, will be a matrix that is 2x1. We have to remember that matrices are not commutative in general. So the product of A times B is not to be expected to be the same product as B times A. Our keyword here is we're looking at associative property, so we're going to add some parentheses in here. If I'm starting out with this, I want to look at K times A, and then we're going to multiply that by matrix B. So I'm going to take the scalar times the matrix, and then whatever the product is there, I'm going to take that new matrix, and I multiply that by B. We want to keep in mind that when we multiply a scalar times a matrix, we get the result that is a matrix. We are going to multiply our scalar by our matrix A. So this is going to kind of look like distributive property. We take every element in the matrix and we multiply it by the scalar. 2 times 2 is 4, 2 times 1 is 2, 2 times 0 is 0, 2 times 5 is 10, 2 times 3 is 6, and 2 times 18 is 16. We get a product that is the same dimensions as the factor that is in our multiplication. The next thing we want to do is take this matrix and multiply it by the matrix B. To multiply these two matrices, we're going to take this top row and set it upright and multiply it by this column. And then once we get those products, we will add them together. 4 times 1 is 4, 2 times 7 is 14, 0 times 5 is 0. So we will get 18 here. And this will be a 2x1 matrix as our product here. We are going to take our second row, set it upright, and then multiply by this column. We have 10 times 1 is 10, 6 times 7 is 42, and 16 times 5 is 80. And we will add those together. The first column we have 2, in the second column we have 13. As a result of this multiplication with this association, we get the matrix 18 over 32. We have the matrix with the entry 18 and 132. starting back with our original given, we would like to associate a different way this time. I want to associate the two matrices together first and then multiply by the scalar. And we want to check to see if it is the same result. So we are going to look at multiplying the two matrices together and then multiplying by the scalar. We've done our check over here to make sure that the multiplication is defined. It is, so we're going to multiply these two matrices. The product of these two matrices will be a 2 by 1. We're going to take this first row and set it upright, multiplied by this column, and then we will add those products. 2 times 1 is 2, 1 times 7 is 7, 0 times 5 is 0, 7 plus 2 is 9. That will be the first entry in our product matrix. Taking our second row and setting it upright, I'm going to multiply it by this column. And then we are adding those products. 5 times 1 is 5, 7 times 3 is 21, 8 times 5 is 40. And then we will add these together. I will have 66 as my entry in this matrix here. We have done the associated part here. Now we need to take this matrix and multiply by the scalar. Again, multiplying by a scalar means that we take each element individually in the matrix and multiply by this scalar number. 2 times 9 is 18, and 2 times 66 is 132. And that is a 2 by 1 matrix. That will be the result here. So we can see that whether we associate this way or this way, we get the same matrix result. So it doesn't matter if we start with the scalar and then multiply the matrix, or if we start with the two matrices and then multiply by the scalar, we get the same result. One oddity in this process is starting again with what we have been starting with as our givens. We can actually take the scalar and multiply by the second matrix first, and then take that product and multiply by the first matrix, and we will get the same result. And this is a weird situation, but it works, and we can demonstrate that as well. So this says that I'm associating the scalar and the second matrix first. So I'm going to take my example of scalar here, 2, and multiply by the second matrix I have. And I will get another 3 by 1 matrix as a result here. And that's this associated part here. Now I'm going to take my first matrix here and attempt to multiply by this product. The first matrix is 2 by 3, the second one is 3 by 1, so it's the same dimensions. So when I multiply A times this product, I will get another 2 by 1, which is what we've gotten the last 2 times. Again, as I've done before, I'm taking this top row and setting it upright. and I'm going to multiply by this column. I will have 2 times 2 is 4. 1 times 14 is 14. 0 times 10 is 0. Adding those together, I will get 18. I'm going to take my second row and set it upright. And I'm going to multiply by this column. I have 2 times 5 is 10. 3 times 14 is 42. And 8 times 10 is 80. Adding those together, I get 132. This matrix is the same matrix as the other two, so even though I have commuted the scalar value and associated it with the second matrix, it still gives me the same result. So, starting with a scalar and 2 matrices, we can do either of these 3 procedures and we will get the same product. So we have looked at the associative property for scalars and matrices. Cheerful calculations.